And so now we move on to the short presentations. And first up is Pamela Jackson, who is part of, I guess she just moved to Cedars-Sinai with Kristen Swanson, and she's now a new independent PI. So welcome. You introduce her.
All right. And I know what my warning song is. I just wanted to thank the organizers for inviting me. This is a wonderful location. I had some time to get out to the beach yesterday, and my mom doesn't know it, but she's about to get some cheap gifts because I was able to find some seashells. She likes them. So in this economy, anything I can find would be great. Um, as it was introduced, I'm going to talk a little bit about our work at looking at distinct transcriptomic signatures that underlie MRI-defined edema patterns in human gliomas. This is some work we've been doing back when we were at Mayo Clinic, working with Columbia University, and now that we're at Cedars-Sinai, we're going to be continuing it. So just a little quick primer. We've talked a little bit about glioma already today. As you know, it's a highly invasive primary brain tumor, resistant to treatment, uniformly fatal. Patients expect a median survival of about 15 months. And MRI is really central to imaging it, visualizing it, diagnosing it, and determining treatment for GBMs. And two main types of MRIs that I think we also talked about a little bit earlier are T1 GAD. And in this image, you see is an exogenous contrast agent that is leaking from the vasculature, known as gadolinium. So T1 GAD. And then T2, we have a T2 weighted image here, which visualizes the edema or the swelling that's at least partly due to that leaky vasculature as well. And so these two images types, as I said, form the basis for a lot of our ability to diagnose. And so you can see these two regions, they overlap. And again, T1 GAD is referred to as contrast enhancing, T2 is the non-enhancing area. And within these regions, we have a lot of tumor cells and we have extracellular space. And this is a micrograph showing in red where the extracellular space is. And even though it's a really, really small region in between the cells, because it's so pervasive throughout, it's making up to about 25% of the volume in the normal brain. And so when edema is introduced, it's increasing that beyond. And for normal tissue, we have what's called the blood-brain barrier, and that's composed of astrocytic foot processes, tight junctions, basement membrane. But as the tumor is haphazardly growing, these tumor vessels are also haphazardly growing, and that's breaking down, and it's allowing a lot of the extravasation of fluid as well as larger molecules like gadolinium to end up in the parenchyma. And so we know that these processes aren't just due to it, growing fast. There's a lot of genomic and epigenomic things that are happening in background as well. And so we want to know what edema can tell us about tumor status. Edema is typically associated, again, with this blood-brain barrier breakdown and tumor aggressiveness. And so we want to explore the relationship between being able to model edema along with the molecular markers. And we want to include sex as a biological variable. And so the question is, how can we quantify this edema, particularly using techniques that aren't advanced MRI imaging, which can be costly, they can be time consuming, and they aren't really useful for historical data or images that have already been acquired. So we know that the hyperintense regions, again, on the T2 weighted MRIs correspond to vasogenic edema in the context of brain tumors. The MRI signal is determined by the properties of the water in the tumor. And these properties can change depending on the abundance of water or interaction with tissue structures present, resulting in different intensities. As you can see in the little cartoon there, you have a much darker intensity where you have less water and a much brighter intensity where you have more. So we want to be able to use non-invasive T2 weighted MRI to capture the tissue in its native state and decipher or deconvolve the underlying microenvironmental characteristics. So I'm not going to, I know it's a math conference, but I'm not going to get into the full extent of the math, but there is a lot of math that underlies MRI equations. I'm just going to talk a little bit about a simplified version of that. where you can see for the signal that you would get from an image is related to the signal without any T2 weighting, and weighted without any T2 weighting or any T2 decay, which you see with the exponential there. And this T2 decay is basically when you get an MRI, they zap you with, it sounds kind of crazy, but they zap you with a RF signal pulse. And when they turn that pulse off, those water molecules, they go from an excited state. And so that's basically what's happening is as it relaxes, we're able to capture the picture along that relaxation path. And so if we start to think about water in multiple compartments or multiple environments, we can then combine those signals into the overall signal that you see on the image. And as I said before, just driving home the point that the more water you have, the brighter the signal will be. And so from that, we're able to build a compartmental model of edema, looking at the overall signal as a composition of the intracellular space and the extracellular space, making some gross assumptions about the characteristics of water between those two spaces. And there's a variety of things that we can do to fit that, but we can even do things as far as try out multiple types of T2s in the intracellular space and extracellular space and see where we get the least error, where did they violate the error the least, because there are certain combinations of parameters that will lead to things where, say, for instance, the fraction of the intracellular space is greater than 1%, greater than 100%. And so that's something that we would see as an error in this case. So moving forward to our study, we had an image-guided biopsy data set that we've been building over several years. We had 55 patients enrolled, 21 were female, 34 male, and 179 image-guided biopsies that were taken. So basically, when the patients go to the OR, the surgeon notates where he's taking the biopsy from on the MRI. And so the biopsies go off for analysis with RNA-seq, and we annotate the MRIs, do various processing to make the maps, and also make sure we're connecting each one of the biopsies to the location on the MRI. And in this case, the edema abundance mean of a region that's about 9 by 9 around that central biopsy location. So we perform gene set enrichment analysis, which is basically just a computational method to detect whether gene sets are different between two different states. And so our states that we're looking at are low and high edema in both male and female populations. So I'm just going to orient you a little bit. For the female population, you'll see where patients were enriched for low edema versus high edema. And on the bottom, you have the different categories of gene sets that were associated with low versus high edema. And we did this in both females and males. Males only had high edema that really set them apart. And what we began to notice in this analysis was that for males, fatty acid metabolism was associated with high edema, but it was associated with low edema for females. And a similar thing began to emerge for oxidative phosphorylation as well. Same thing, it was associated with high edema for males, but low edema for females. And so we're really curious about what is underlying or driving this. So that led us to do a leading edge analysis, which is basically where you're identifying the influential genes within each gene set. And so we did this again for males and females. And we saw a number of differences, and I'll just kind of go through this here. We saw a number of differences. And one in particular that stood out to us is kind of small. I hate how small that is on here, but IDH1 in particular showed up. It showed up for males in both cases as a male-only gene analysis. And this is particularly interesting because mutations in IDH1 lead to a very favorable prognosis for cancer patients in general, which is interesting because being a male isn't a protective characteristic. You actually have worse prognosis. So it'd be interesting if we could find out more about what's happening there in particular. So in summary, we defined an image-based model to estimate edema based on T2 weighted images. We utilized RNA-seq from image-guided biopsies to better understand associated with edema and examine sex differences. Two pathways in particular stood out: fatty acid metabolism and oxidative phosphorylation. We identified sexes as distinct in gene set enrichment analysis. And looking at our leading edge analysis, we identified IDH1 in particular as something that was significant as a leading edge gene. So our initial analysis suggests that sex differences should be further explored for edema reduction treatments or metabolic targeting therapies. So with that, I just want to thank our funders. And I have two quick announcements I want to make. First, the Digital Twins for Health Society is a new society I'm a part of, and we are having our inaugural annual meeting in Houston early next year. And the deadline for any abstracts is November 10th, so just a couple of weeks. And you can see at the bottom dt4hs.org. And then the second announcement is that Cedars-Sinai has a brand new PhD program in health artificial intelligence as a part of the Department of Computational Biomedicine. Those applications are due early next year as well. And if you need a brochure or a QR code or anything, you can come see me or Kristen any of the breaks. So thank you. Any questions?
Perfect. Thank you so much. Any question for Pamela?
That was really interesting. Thank you very much. I'm not sure if I missed the age of your patient, and I was wondering if you had that in children as well, I guess in kids.
So no, we didn't include children in this analysis. They do get various types of glioma, but not necessarily glioblastoma as much as adult patients do.
Okay, so I was kind of curious if the sex difference had something to do with hormone things as well, or...
That's a good question. That's a good question. I don't think we haven't found anything in particular on that, but we will certainly be looking for that as well.
Thank you.
Any other question? Okay, thank you so much, Pamela.